This is the first video in the chemistry of gases lesson. Our first series of videos for this unit will be on the kinetic molecular theory and gas behavior. Here is our learning target for these first few videos. As you can see, it says I can use the kinetic molecular theory, otherwise known as KMT, to explain gas behavior and properties. There are some sub-targets here, and throughout this first video we will be focusing almost entirely on this first statement here, gases 1A. We want to be able to relate the mass of a gas to its temperature, average velocity, and rate of diffusion using Graham's law. The next sequence of videos will continue to explore the rest of these sub-targets. So first I want you to ask yourself, what is a gas? What do you think of when you see the word gas? What makes a gas a gas? Think about those questions. And once you have thought about them, go to YouTube and watch this video. You can see the address here. I also linked it for you on Classroom. I labeled it Primer Video 1, just like you see here. It's only about a 2-minute video. So once you've had a chance to think about these questions, go ahead and watch this video and then come back to the lesson here and click play. So you've had a chance to watch the video on what is a gas, and you've seen some different properties of gases that we can explain based on the particle nature of the gases, which is what this video is all about. So to start with, we will explore the kinetic molecular theory, or again called KMT, of gases. There are 3 points to this kinetic molecular theory. The first point: gases consist of tiny particles with large separations. So the ramifications of this would be that most of a gas's volume is actually empty space. Most of a gas, there's really nothing there. Now, what some students struggle with is they think, well, there's particles, but then there's air between the particles. Well, remember, the gas itself is the air. Those particles themselves are the air. So when those particles are far apart, what's in between those particles is nothing. There is nothing between those particles, so it's mostly empty space. And this would even be true for gases that are made of larger particles. In other words, the particles have lots of atoms in them. Even these larger particles, if that substance is a gas, there's still a huge majority of the volume is empty space. The second point of the KMT is that these gas particles are in continual, rapid, random motion. Because of their motion, these particles, they will collide with one another. They'll also collide with their container. In other words, this allows gases to always fill their container, because as they move around, they are going to move until they hit something, whether it be another particle or the container that's holding it. The last point of the kinetic molecular theory is that gases at the same temperature have the same average kinetic energy. And this really doesn't just apply to gases. This is really a definition of temperature, average kinetic energy, which we'll explore on the next few slides as well. But the point here is that, again, kind of like we said on the previous point, is that this is regardless of the mass of the particles. Doesn't matter how massive the particles are, doesn't matter how many atoms are in it. If we have 2 gases at the same temperature, their particles will have the same average kinetic energy. So let's keep exploring this idea of temperature and kinetic energy. First, a definition, which we've already seen a little bit with our thermochemistry unit, and we just mentioned it on the last slide. Temperature, which we often use the capital letter T to denote, is simply the average kinetic energy of particles in a substance. Kinetic energy, which we typically use the symbol E with the subscript letter K, E for energy, subscript K to denote as kinetic, is simply energy of motion. Any particle, whether we're talking about an individual atom or if we're talking about a planet, if any particle or object is in motion, it will have kinetic energy. To calculate kinetic energy, we use the equation 1/2 mv squared, where m is the mass of the particle or object and v is the velocity of that particle or object. So if we wanted to put the definition for temperature in an equation, it would look like this, where temperature, capital letter T, is equal to EK or KE as I have it written here. And then you might recall from math class, if you say a bar over a symbol like you're seeing here, that means we're taking the mean or the average of that value. So temperature equals average kinetic energy. Or in other words, we could say the temperature of a substance is equal to 1/2 the average mass of its particles times the average velocity squared of its particles, because kinetic energy is 1/2 mv squared. So average kinetic energy would just be 1/2 the average mass times the average square of the velocity. Now we can simplify this, and we can not worry, we don't need to worry about the mass being average, because if we have a pure substance, for example, if we're talking about oxygen gas, every particle in that sample is the exact same mass. So we don't need to worry about the average mass because all those particles are exactly the same. So in other words, we can say that the temperature of the gas would be 1/2 the mass of its particle times the average velocity squared. Because we need to remember that these particles, while they're all moving around, they're not moving at the same speed all the time. Some are moving fast, some are moving slow, so we take their average. So let's apply this idea to two different gases. So say we have this situation. Samples of helium and neon gas are both at 25 degrees Celsius, so they're at the same temperature. Which particles have the greater average velocity? So here's what we're told. We're told that the two temperatures are the same. The temperature of the helium gas is equal to the temperature of the neon gas. Based on the previous slide, we know that that means the average kinetic energy of the helium particles must equal the average kinetic energy of the neon particles. And taking that a step further, we know that kinetic energy is 1/2 mv squared. So the average kinetic energy of the helium particles would be 1/2 the mass of the helium atom times the average velocity of those helium atoms squared. And that would equal 1/2 the mass of the neon atoms times the average velocity of the neon atoms squared. Now we can simplify this equation because 1/2 appears on both sides, so it would cancel or drop out, and you can see what we're left with. Now you might be wondering, well, how will I know which particles are traveling faster on average? Well, here's the thing. We know the masses of these particles. We can look up the molar masses of helium and neon, or we could think about the mass of an individual atom. It's probably easier just to look at the molar masses. And if we look at the periodic table, we'll see that the molar mass of helium is 4 grams per mole, and that of neon is just over 20 grams per mole. So if we think about this, if these two sides are going to be equal to each other, the only way for that to work is for the average velocity of the helium to be greater than the average velocity of the neon. That's the only way the left side can equal the right side, because the helium mass is lower. So to answer this question, which particles have the greater average velocity, it's the helium particles. But in general, we don't just have to apply this to helium and neon. We can simply say that at the same temperature, and remember, it has to be at the same temperature because we have to have the same average kinetic energy, that at the same temperature, lighter gas particles have a greater average velocity. So we've had a chance to look at how temperature and kinetic energy play a role in gases and their behavior. Let's take a look at some other behaviors and properties of gases. The next few slides, you'll see a scenario or something I want you to consider. And then once I do ask you to consider, pause the video and think about that for a second, and then play it and see the explanation. So our first thing I'd like you to consider here is this. The density of liquid water at 4 degrees Celsius is 1 gram per milliliter. But yet if we had water vapor, the density of that at the same temperature, as long as we're at standard atmospheric pressure, is 0.792 grams per liter, or in the same unit, 0.000792 grams per milliliter. So in other words, this water vapor is over 1,250 times less dense than liquid water at the same temperature. So here's what I want you to pause the video and consider. Why is the density of the water vapor so much lower than the liquid water? So if you recall our kinetic molecular theory and the points that we made on that first slide of the lesson, you'll recall that most of the volume of a gas is empty space. There's nothing there. So when we have water vapor, there's very little mass in any given volume of that water vapor, or for any gas for that matter. Thus, the density of a gas is way, way lower than that of a solid or a liquid, simply because there's so much empty space between the particles. All right, next one I'd like you to consider. So if you take a balloon and fill it with sand, you can manipulate it, squeeze it with your hands, fingers. You can manipulate the shape of the balloon, but yet the sand itself still occupies the same volume. Whatever volume of sand's in there, it's still going to be the same volume. Yes, you'll change its shape, but it's still the same volume of sand. You do the same thing with a gas that you've put in a balloon. You can take that balloon and you can squeeze it down, and that gas will actually occupy less space. It decreases the volume of the gas. So I want you to consider, why can you compress a gas? Why can you make its volume smaller, but not a solid or a liquid? So hopefully your thinking went back really to what we said on the last slide. And it goes back to that large amount of empty space between the particles of a gas. Because there's so much empty space between the gas particles, you can move them closer together. There's just way more room that they can be shoved closer together, which allows you to reduce the volume of a gas. In other words, to compress it. If we have a solid or a liquid, those particles are already quite close together. There is no room to push them any closer to reduce the volume, so we really cannot compress a solid or a liquid. Another consideration. Say I had 250 centimeters cubed, that would be the same thing as 250 milliliters of zinc, and I put that in a 500 centimeter cube container. You're still only going to have 250 centimeters cubed of zinc. That zinc is still going to occupy the same volume. It's fixed by the amount of zinc that you have, by its mass. But yet, if I do that same thing with a gas, so say I had gas in a 250 milliliter container, and then that container expanded to 500 milliliters. It doubled in size. The gas is now going to have a volume of 500 milliliters. It will occupy that entire space. So why do gases expand to fill their entire container? Thinking about the kinetic molecular theory, you'll remember that the particles that make up a gas, they're in constant motion. They will continue to move until they collide with something. That something can really be one of two things. It can either be another gas particle, or it can be the container they're in. So as that container expands, the particles that are in it, if assuming it's a gas, will continue to move along with the container until it collides. So the volume of the gas expands right along with the volume of the container. If we're talking about a solid or a liquid, those particles are not freely moving like that. They're essentially bound to each other, where they're not going to break free and run into the container. So in other words, solids and liquids, they don't move until they collide with the container. So their volume is fixed by their mass and density. Another thing to consider. Suppose you go home today, you walk into your house, and you smell fresh baked cookies as soon as you walk in the door. How would it be possible that you can smell those cookies even though, depending on the layout of your house, you might be several rooms away from the kitchen? Well, this goes back to the motion of the particles, just like we said on the last slide. The particles that are responsible for that cookie odor are gases. Essentially, when you smell something, particles of a gas are entering your nasal cavity, and it hits the sensors up there, and voila, your brain interprets it as a smell. due to the random motion of any gas particles, those gas particles that are produced from the baking of the cookies, they're going to move through the other gases that are in the air of your house. So regardless of where you are in the house, assuming you don't have a gigantic house, you will be able to smell this odor as those cookies are being baked. This brings up the term diffusion. The term diffusion simply means we have one material moving through another material. So in this case, we would say the gas particles produced by the cooking or the baking of the cookies are diffusing through the air in your house. Another situation that's kind of similar to this diffusion would be something like this. Let's say your bicycle tire has a really tiny hole in it, super, super tiny, but you don't know it. In fact, you're maybe even riding it and it seems normal, but over time, obviously your tire is going to go flat. So why is that? Why does the tire go flat? Well, again, this goes back to the motion of the particles. Those particles that make up the gas in the tire are randomly moving around. Just based on their random motion, some of them are going to hit that opening. They're going to hit that tiny hole, and they're going to leave the tire. When that happens, it's going to reduce the number of particles in the tire, and it'll eventually go flat. This scenario is called effusion. So we had diffusion as one material moving through another. Effusion is a little more specific. That means we have a gas escaping through a small opening. Alright, so this whole idea of effusion leads us to what we call Graham's law of effusion rates. Graham's law of effusion rates says the following. It says that the rate of effusion for a gas is inversely proportional to the square root of its molar mass. Now I know that's kind of a mouthful and it might not make a whole lot of sense. So here's another way of looking at it, a mathematical way of looking at it. This actually says the exact same thing as the sentence above, where we have the rate of effusion of a gas, and this symbol here is a proportion, and because it's proportional to 1 over something, that would be inversely. So the rate of effusion of a gas, meaning how quickly does this gas escape a small opening, is inversely proportional to the square root of its molar mass. In other words, if we were to double the square root of the molar mass, so change the molar mass, so whenever we take the square root of it, it's twice as large, that would cut the effusion rate in half, because that's what the whole inversely proportional means. I double one, the other one gets cut in half. So you might be thinking, geez, that seems really obscure. How am I going to use this? Well, it's best used in this scenario, not for any single gas, but for comparing the rates of effusion rates of two gases. And if I combine that proportionality for two gases, we would get this equation. And this is not an equation I need you to memorize. I will give it to you. But what it tells us is this, is that the ratio of the rates of effusion for two gases, so we'll just call the gases A and B, the ratio of those rates, rate A compared to rate B, would be equal to the square root of the molar mass of B over the molar mass of A. Notice that due to the inverse proportionality that we talked about up here, the gases and their rates are on opposite sides of the fraction. So if we are finding the rate of A compared to the rate of B, our molar masses would be molar mass of B compared to A. You can see how those get flipped there. So let's see if we can use this equation in an actual problem. So here's the question. Ammonia, NH3, and hydrogen chloride, HCl, gases are mixed in a container with a small opening under the same conditions. That whole same conditions, when we're referring to a gas, really is talking about temperature and pressure. So even though we don't know the temperature and pressure of these two gases, what we do know is that they're at the same temperature and they have the same pressure. So there are actually two questions here. Which will effuse out of the opening at a faster rate, and determine the ratio of effusion rates for the gases? Well, for that first question, there isn't a whole lot of calculation to do. Recall from earlier in the lesson, we looked at how the mass of a gas can be related to its average velocity. Because these two are under the same conditions, All we need to do is we need to determine their molar masses, and we can say which one will effuse faster. So if you look up the molar masses, or calculate them really, you'll find the molar mass of ammonia is 17 grams per mole, and that of hydrogen chloride is about 36.5 grams per mole. So thinking about what we learned earlier, we learned that a lighter gas will travel faster on average. So this ammonia, the ammonia particles will be moving around faster on average than the hydrogen chloride particles are, because the ammonia is lighter. So what that tells us then is the ammonia will effuse faster, because its particles move faster on average. So we've really already answered the first question there. So the second question, we're asked to determine the ratio of effusion rates. Now I left the molar masses here, because now we're going to need to use Graham's law and that ratio of effusion rates. So what we're asked to find is this ratio here of the rate of ammonia compared to the rate of hydrogen chloride. You could do it the other way around. It really makes no difference. I always prefer to put the lighter gas on top, because that's the one that effuses faster. So based on Graham's law, I know that that ratio will equal the square root of the molar mass of the hydrogen chloride divided by the molar mass of the ammonia. Note the symbol here, the capital letter M, is often used for molar mass. So now I just need to plug in our molar masses here. So the ratio would be the square root of 36.46 grams per mole divided by 17.04 grams per mole. Notice that the units are completely going to cancel here. Grams will cancel, moles will cancel, and whenever you're finding a ratio, this is very common that that ratio is unitless, because we're comparing two of the same value. We're comparing the rate of effusion for both, so we'd expect that they'd have the same unit and they would cancel. So when you do that calculation, you will get 1.463. Now, a quick note about this: whenever you do a calculation like this, make sure that you write it so we know which ratio you're finding. In other words, we could just as easily find the ratio of the rate of HCl over the rate of the NH3, and you would get a different answer. So you need to make sure you indicate which one you're actually finding. So what this tells us is that the ammonia, the NH3, effuses 1.463 times faster than that of the hydrogen chloride. Alright, let's look at one more example of Graham's law of effusion rates. Different sort of question here. We have a gas whose molar mass you wish to know effuses through an opening at a rate 1/3 as fast as that of helium gas under the same conditions. There's that whole same conditions thing again. What is the molar mass of the unknown gas? So let's consider what we're told here. We're told that the unknown gas effuses at 1/3 the rate of that of helium. So in other words, it's slower than helium. Or another way to look at it is helium is effusing 3 times faster than the unknown. So we can write that the rate of effusion of the helium is equal to 3 times the rate of the unknown gas. Using Graham's law, we can write an equation to relate the rates, the ratio of them. Again, I like to put the faster one on top. That's my preference. I know helium is going to go faster based on what we're told. So the rate of helium compared to the rate of effusion of the unknown will equal the square root of the molar mass of the unknown over the molar mass of the helium. Now notice we're asked to find this molar mass of the unknown. That's what we're looking for. So I want to solve this equation for that, the molar mass of the unknown. So the first thing I want to do is get rid of this square root. So I'm going to square both sides. That'll get rid of the square root. So on the left side I have the ratio of the rate of the helium compared to the rate of the unknown squared will be equal to the mass of the unknown divided by the mass of the helium. So to get the mass of the unknown by itself, I'm going to multiply by the molar mass of the helium. That'll get it to the other side. So that gives me the molar mass of the unknown equals the molar mass of the helium times the square of the rate of the helium over the rate of the unknown. And then going back to our initial equation we wrote there, this ratio we already know. Because we know that the helium's effusing 3 times faster, the rate of the helium divided by the rate of the unknown will equal 3. So now it's just a matter of plugging in some numbers here. I look up the molar mass of helium. It's 4.00 grams per mole. Multiply that by 3 squared. So 4 times 3 squared, or 4 times 9, is 36. So 36.0 grams per mole. And we would expect it to be much heavier than helium, because remember, if it's heavier, that means it's going to be moving slower on average. So it will effuse at a slower rate. So going back to our learning target slide here, this first lesson, we have looked almost entirely at this first sub-target here, wanting to relate the mass of a gas to its temperature, average velocity, and rate of diffusion using Graham's law. Our future lessons here will start to pick up on some of this other stuff.